Now let's consider the equation y double prime minus y equals tangent of t. We might want to try to find a trial solution for a particular solution that would satisfy this. But we're going to run into problems if we do that, because the question becomes, what kind of things would we take first and second and higher derivatives of in order to end up with a tangent of t? Now the problem's illustrated. Well, first let's just put this in context. If this was a cosine t on the right side, as we've seen, we wouldn't have any problem, because a cosine of t comes from the derivatives, comes from the derivatives of sine and cosine functions. If it was an e to the kt on the right hand side, an e to the kt comes from derivatives of e to the kt. If it was powers of t on the right hand side, some power or some combination of powers, powers of t come by taking derivatives of powers of t. But tangent of t doesn't come from taking higher derivatives of any particular function. Now, we can integrate the tangent of t once. The integral is the natural log of the sine of t. So we could have a trial solution perhaps that had multiples of natural log of sine of t and tangents of t. If we had second derivatives, as we do here, we'd have to have something else. And what would we take a derivative of in order to get the natural log of sine of t? Can we integrate the natural log of sine of t in closed form? I don't think so. So we run into problems, whereas if it's a cosine, we can use multiples of sine and cosine. If it's an exponential, we can use multiples of an exponential, perhaps with some powers and so forth. If it's powers of t, we can use powers of t. If it's tangent of t, we don't know what to use. So here's a case where our method of undetermined coefficients, the common sense method of looking for a trial solution with some constants that can easily be evaluated, isn't going to work so well. Another example of where things might not work very well. If we had an equation like y double prime minus ty equals cosine of t. Now, if it wasn't for the t here, we'd be fine. We'd be back to an equation we've already seen. Y double prime minus y equals cosine of t is not that difficult to solve. We could try the same thing we tried before, try a particular solution, a sine of t plus b cosine of t. And if we plug that into the equation, we end up with this, negative a sine t minus b cosine t plus ta sine t plus tb cosine t equals cosine t. Well, if you're not thinking too far ahead, that doesn't look so bad. We just bring all the coefficients of the sine together. We get negative a plus t is the coefficient of our sine. And the same thing for the cosine, negative b plus t is the coefficient. And now the coefficient of the cosine here has to equal the coefficient of the cosine here. So it looks like negative b plus t should equal 1. There's no sign on this side, so that negative a plus t should equal 0. Therefore, a equals t and b equals 1 plus t. You might not yet see the problem with that, but now we would then come up with yp equals t sine t plus 1 plus t cosine t. Yp prime, well, we'd have to apply a product rule here. We'd have sine t plus t cosine t. And here we'd have cosine t plus 1 plus t multiplied by negative sine t. That doesn't look anything like the derivative of this. And the reason it doesn't, and think about the reason for a second. Okay, if you take the derivative of this, you're going to get a cosine t minus b sine t. Down here you've got 4 terms. How did that happen? Well, the problem is that t isn't constant. remember we assumed that A and B were constants. So there's a problem here. T isn't constant, so A and B aren't constant. Okay, so when we did this solution here, we didn't get constants, and that contradicted our assumption that we had constants here and led to a big mess that isn't going to be at all helpful.